This is an AQA GCSE Trilogy paper, higher tier physics paper 1H from June 21. Starting with question 1. Figure 1 shows a mobile phone with its battery removed. A student measured the potential difference across the battery and then put the battery into the phone. What is the equation linking current, potential difference and resistance? If you've been following me for a while, you know I like using mnemonics with formula triangles. This one is vets in rain. So if we look down our options, if we cover what we're after, so current, it's voltage or potential difference divided by resistance, which is why that's not correct. Resistance is given by potential difference divided by current, which is why that's not correct. What about this equation? Cover V, yes, it's I times R, which is why that's right. 1.2, the current in the electronic circuit in the mobile phone was 0.12 amps. The potential difference across the battery was 3.9 volts. Calculate the resistance. So if we have a look, we're after resistance, which is voltage divided by current. We know our voltage is 3.9. Our current was 0.12, so our resistance is 32.5 ohms. Write down the equation which links energy, power and time. You need this formula triangle here. So we can see that energy equals power times time, or you can write it out in letters. The battery was fully charged when it was put into the mobile phone. The battery discharged when the mobile phone was switched on. The average power output of the battery as it discharged was 0.46 watts. The time taken to fully discharge was 2,500 minutes. Calculate the energy transferred. So we need this equation. Be careful with your units. We need this in seconds by timesing by 60. So that becomes 150,000 seconds. So we know we have 0.46 watts. We don't need to touch that because that's the standard unit. Our time value is now also in the standard unit of seconds. So our final answer here is 69,000 joules. The mobile phone includes a sensor to monitor the temperature of the battery. Figure 2 shows the circuit symbol for this component. What component does the circuit symbol shown in figure 2 represent? I always call this the hockey stick component. It's a temperature dependent resistor, a thermistor. The temperature of the component in figure 2 increases. The potential difference across the component remains constant. Explain what happens to the current in the component. Remember that a thermistor is unusual in that as the temperature increases in a thermistor, the resistance decreases. And therefore, the current will increase as a result of that resistance decreasing. A radioactive source emits alpha, beta and gamma. An alpha particle is the same as a helium nucleus. How many times bigger is the radius of a helium atom compared to the radius of an alpha particle? Be really careful here. We're comparing these two things here. So remember that a nucleus is found in the centre of an atom, and it is very small compared with the size of the atom, because remember all those shells of electrons make the atom much larger. So in this case, how many times bigger is the radius of a helium atom compared to the radius of an alpha particle? Well, it is much, much bigger. In fact, it's more than 10,000 times bigger. Alpha particles can ionize atoms in the air. What happens to an atom when it is ionized by an alpha particle? Remember that an alpha particle is made up of 2 protons and 2 neutrons. So when the atom is ionized by an alpha particle, by definition, the atom loses, and because an electron is negatively charged, it becomes a positive ion. A spark detector is a device that can be used to detect alpha radiation. A spark detector works by alpha particles ionizing atoms in the air near a wire mesh. A large potential difference creates a spark when the air near the wire mesh is ionized. Suggests why a spark detector cannot detect beta radiation. Because this is all to do with the ionizing power, remember that alpha is very ionizing and beta is nowhere near as ionizing. So actually you find that the beta can't ionize those atoms enough. A teacher wants to demonstrate that the radioactive source emits alpha, beta and gamma radiation. Figure 3 shows the equipment the teacher has. So we have 3mm thick aluminium sheet. Remember, aluminium stops beta radiation getting through. A thin sheet of paper. Remember, that stops alpha. We have a radioactive source and a holder, a radiation detector and a count rate meter. Describe a method the teacher could use, and that is worth 6 marks. So first of all, we need to find the background radiation levels. And record count rate. Next, place the detector very close to the radioactive source. And record count rate. Now we need to take it in turns to put these different types of material between the source and the radiation detector. So place paper between source and detector. Record count rate. If there is alpha radiation, the count rate will drop. Why? Because it's stopped by the paper, it can't penetrate through. Because alpha can't penetrate paper. Replace paper with aluminium foil. Again, record the count rate. This time, if you have beta radiation, the count rate will decrease. Why? Because beta can't penetrate through aluminium foil. If you have gamma radiation, there'll be no change in the count rate with either paper or aluminium foil because gamma is very penetrating. Running out of space here. So remember, you're using this apparatus to determine what type of radiation you have, and it's always good to repeat and calculate a mean. Always put that in. Figure 4 shows a sailing boat crossing an ocean. There is a wind turbine on the boat. The wind turbine generates electricity to charge a battery on the boat. Name one other renewable energy resource that could be used on the boat to generate electricity. So pick something sensible. You could easily place solar panels here. Don't be saying things like hydroelectric because obviously you need a dam for that. You could also put biofuel or wave power. The boat also has a generator that burns a fossil fuel. The battery can be charged by either the wind turbine or the generator. And then why is it useful to have the combination of the wind and the generator? Because Having the wind means that less fuel is being burnt, which has less of an environmental impact. Explain one environmental impact of using fossil fuels to generate electricity. Well, when you burn fossil fuels, it releases carbon dioxide, which is a greenhouse gas that contributes to global warming. So that causes polar ice caps to melt, rise in sea level, habitat destruction, etc. You could also mention burning fossil fuels helps release sulfur dioxide into the air, which causes acid rain. The kinetic energy of the boat is 81 kJ, which is the equivalent of 81,000 joules. The mass of the boat is 8,000 kilos. Calculate the speed of the boat. So we've got a mass, we've got an energy, we're after speed. The equation we need is KE equals half mv squared. I knew to convert this unit here. We're using standard SI units throughout. So that's 81,000 equals half times the mass times v squared. Let's sort out the right hand side first of all. To get v squared on its own, we divide both sides by 4,000. And then finally square root to find v. To get 4.5 as your final answer. As the boat passes over a wave, the gravitational potential energy of the boat increases by 19,600 joules. The mass of the boat is 8,000 kilograms. Gravitational field strength is 9.8. Calculate the change in height. So we need GPE equals mgh. What's our energy? Well, it's 19,600. Our mass is 8,000. Gravity, we're told, is 9.8. We're after h. Sort out the right hand side by doing 8,000 multiplied by 9.8. And then divide both sides by 78,400. So our change in height is 0.25 meters. A student determined the density of a cube made out of bronze. The student used a balance to measure the mass of the bronze cube. Figure 5 shows the balance before the cube was added. What type of error is shown on the balance? Okay, if it's showing a number before anything's been added, it's a 0 error. How could the student get a correct value for the mass of the cube from the balance? Either reset the balance to 0 grams or subtract the reading shown on the balance from the reading taken. The student measured the length of the bronze cube using vernier calipers and then using a micrometer. Complete the sentence. The results in table 1 show that the vernier calipers and the micrometers have different, the answer here is resolutions. Look what they measure to the nearest. The student wanted to determine the density of a bronze coin. The student had several identical coins. The volume of each coin was very small. The student added water to a measuring cylinder. Figure 6 shows the student reading the volume of water in the measuring cylinder. Give 2 changes the student should make to increase the accuracy of the volume measurement. Okay, this is a nightmare. Look at that measuring cylinder. It's completely wonky. It needs to be placed flat on the horizontal surface. And remember, you always read at eye level at the bottom of the meniscus to avoid issues with parallax. Describe how the student could use a displacement method to determine an accurate value for the volume of a single coin. So we've been told that the volume is very, very small. So that means it makes sense, therefore, for us to measure the volume of lots of coins and then divide to find the volume of a single coin. So what do? We add, let's say, 10 coins to a measuring cylinder. After all, we're using a displacement method. Measure the change in water level in the measuring cylinder. And then finally, divide by 10 to get an accurate volume for a single coin. Old penny coins were made from a disc of bronze. New penny coins are made from a disc of a different metal. Table 2 shows information about the discs used to make each coin. The discs used to make the old and new coins have the same cross-sectional area. Calculate value x in Table 2. Give your answer to two significant figures. The volume of a disc can be calculated using the equation. Volume of a disc equals cross-sectional area times thickness. So we're being asked fundamentally to find the density of the new penny, but that's going to take us a lot of working out. After all, this question's worth an awful lot of marks. I've set myself up by copying the equation they've given us and also naming the fact that density equals mass over volume. So we're not ready to touch the new penny yet. We're going to have to start by working out the cross-sectional area of the old penny. I'm going to use red to show that we're talking about the old penny, because then I'll be able to work backwards based on the fact that the cross-sectional area of the new penny is the same. It will allow me to find the volume and then substitute it into this equation over here to finally find the density. But let's get going. So number 1, we are after the cross-sectional area of the old penny. So the first thing we need to do is find its volume using density equals mass over volume. We know its density was 8.9, its mass is 3.6. We're after its volume, which is x. So do 3.6 divided by 8.9 to get 0.404 as our volume. So that is the volume of old penny. I'm going to lay it all out for you. Then we can use this equation to find its cross-sectional area. So let's steal that equation again. So we know its volume is 0.404. The cross-sectional area is what we're after. Let's call it A. We know its thickness is 0.16. Divide both sides by 0.16 to find the area, which becomes 2.528. So that's the area of the old penny. And then look here, they said that the old and new coins have the same cross-sectional area. So again, using this equation here, I'm going to change colour because we're now looking at the new penny. We're going to look for its volume by taking the cross-sectional area that we just calculated for the old penny, multiplying it by the new penny's thickness, which is 0.17, to get a volume of 0.42977. And believe it or not, we're finally ready to find its all-important density, which remember is given by mass divided by volume, and all that work went into finding the volume. We know that its mass is 3.6. There's its volume, put that into your calculator, and then your final answer to two significant figures was 8.4. Just going to steal this working. And there you have it, an awful lot of working, but it is worth 5 marks. A TENS machine uses an electrical current to relieve pain. Figure 8 shows the electrodes on a TENS machine connected across an ankle. The maximum power of the TENS machine is 240 MW. The potential difference across the battery in the TENS machine is 2.5 volts. Calculate the maximum current from the battery. So we have power, effectively voltage, and we're after current. So we want the formula triangle, which is PIV. So we can see that current is given by power divided by potential difference of voltage. Just make sure you get that 240 MW into watts by dividing by 1000. So it becomes 0.24. And then divide by the voltage, which was 2.5. And once you've done that, you'll get a current of 0.096 amps. Figure 9 is a sketch graph showing how the potential difference across the electrodes varies with time. A student concluded that there was an alternating potential difference across the electrodes. How does figure 9 show that the student was not correct? Okay, you'd expect if it was alternating for it to also appear in the negative side of this y-axis here. So you'd expect those graph lines to dip down. Because the potential difference is always positive, it means that it can't be an alternating potential difference. Figure 10 shows a circuit the student built using the battery from the TENS machine. So here we have a variable resistor. This is a regular resistor, a fixed resistor, our ammeter measuring current, voltmeter measuring potential difference, and our battery. The student recorded how the current in the resistor varied with potential difference across the resistor. Figure 11 shows a sketch graph of the results. What relationship does figure 11 show? You can see here, because it passes through 0, that there is a directly proportional relationship between potential difference and current. You can see that's a straight line as well. It's linear. Figure 12 shows two more circuits that the student built using the battery from the TENS machine. The resistors all have the same resistance. Compare the readings on the voltmeter and the ammeter in circuit A and circuit B. In order to answer this question, first of all, we need to consider the voltage and current rules for series versus parallel circuits. So over here, I've shown that this is a series circuit, and remember that the voltage is shared between components in a series circuit. Now, because we've only got one component in this circuit, the fixed resistor, we can really say that all the voltage is going to be there. So let's say for argument's sake it's 10 volts. But what about over here where we have a parallel circuit with the extra branch? Well, here the voltage is the same. And so if we had 10 volts passing here, we'd also have 10 volts there. So in terms of answering this question, what is true about the readings on the voltmeter? We'd say that the readings are the same for both circuits. Things become slightly different when we consider what's going to happen at the ammeter, which measures current. Because look, here's our formula linking voltage, current and resistance. Now we've been told that the resistors all have the same resistance, so this value stays the same. We've already made a comment about the voltage readings, so what does that mean must be true about the current readings? Well, if the voltage is staying the same here and the resistance is the same, what does that mean for the current reading? Well, it must actually be double in circuit B compared with the reading of that ammeter in circuit A. An air source heat pump transfers energy from the air outside a building to increase the temperature of the air inside the building. Figure 13 shows an air source heat pump. The compressor is connected to the mains electricity supply. The pipe in the heat pump contains a substance called coolant. In the evaporator, energy is transferred from the air outside the building to the liquid coolant. The temperature of the coolant increases and it evaporates. Explain what happens to the internal energy of the coolant as the temperature increases. So think about this in terms of particles. Well, the kinetic energy of the particles increases. And then we need to make a statement about the internal energy. Well, this is also going to increase. Why is that? Because it is the sum of both the kinetic and potential energy of the particles. So there's kinetic energy and potential energy. What name is given to the energy needed to change the state of liquid coolant? So that change in state means that it is the latent heat of vaporization. So that's turning something from a liquid to a gas. What happens to the mass of coolant as it evaporates and becomes a vapor? It's actually going to stay the same. The compressor increases the density and temperature of the coolant vapor inside the pipe. Explain why the pressure in the pipe increases. This is linked with collision theory and chemistry, again to do with kinetic energy. Because the temperature of the coolant has increased, it means that there are going to be an increased frequency of collisions with the wall of the pipe, meaning that there's a greater force per second. And remember, pressure is given by force over area. So if force increases, pressure by definition increases, and always state an equation where possible. The condenser transfers energy from the coolant to the air in the building. When the total energy input into the heat pump system is 1,560 kJ, the temperature of the air in the building increases from 11.6 degrees Celsius to 22.1. The efficiency of the heat pump system is 87.5%, and the mass of the air inside the building is 125 kilos. Calculate the specific heat capacity of the air in the building. Give your answer in standard form, and it is worth a beastly 6 marks. So we're being asked to find the specific heat capacity, which means we need to use this equation, Q equals mc delta T, because that's going to help us find C, which is the specific heat capacity. We have our mass, which is 125 kilograms. What about our change in temperature? Well, that's the difference between these two numbers, which is actually 10.5 degrees. However, we don't have enough information yet to find Q, because we've been told there that the total energy input is 1,560 kJ, but to use Q appropriately, we need to find out the useful energy output. And so we need the equation which states that efficiency equals useful energy out over total energy input. So we know the efficiency is 87.5. Let's turn that into a decimal, so that becomes 0.875. We're after the useful energy output, and then the total energy input, we were told, is 1,560 kilojoules, but be careful with your units. Look, that final unit is in joules, so times by 1,000 to sort out any issues there. Then do 156 followed by 4 zeros times by 0.875 to find your useful energy output, which is 136530. And now we're ready to use Q equals MC delta T. We have all the relevant information. The mass we were told is 125 kilograms. We're after C, the specific heat capacity, and we worked out the change in temperature was 10.5. Let's simplify the right-hand side by doing 10.5 times 125. And then finally, to find specific heat capacity, divide both sides by 1,312.5. To get 1,040, do not lose that final mark. We need it in standard form. It becomes 1.04 times 10 to the 3. The air in the building gains 400 joules for every 100 joules of energy transferred from the mains electricity supplied to the compressor. An advertisement claims that the heat pump system has an efficiency of 400%. Explain why the advertisement is not correct. Okay, well, it's making a lot of assumptions, that advertisement. First of all, that the efficiency is 100%, which clearly it can't be. Secondly, the advertisement has ignored the energy input from the surrounding air. And so really what that means is that the total energy input must be greater than the energy supplied from the electricity. So lots of false claims here.